Okay, continuing on. So we were looking at the sodium dichromate, and you can perhaps see that sodium, which is group 1, will always be present as an Na plus. So Na plus is going to be, this guy is going to be plus 1. And if we know that, and we know that oxygen is going to be negative 2. So if we were to determine that for chromium, you can simply say that 2 times 1, which is plus 2, plus 2 times x plus 7 times negative 2, and this all has to total up to 0. And so you would say that 2x um, minus 12 is equal to 0. Adding 12, that should be a minus. Adding 12 on both the sides and then solving for x, you can simply say that x will come out to be 6. So the chromium here will come out to be plus 6. When you continue on with SnCl4, you can perhaps see that tin is present as a plus 4 binary compound, and chlorine is a negative 1, and those will be their oxidation states respectively. So I want you to work on the remainder, which is basically 2 or 3 of these problems, and I'm just going to write down what the answers should come out to be. For manganese, you should get a plus 7, and if you don't get that, then please see me, because then of course you haven't really figured out how to go about that. In case of FeSO4, sulfate is to negative. That means Fe must be plus 2. Let's write that again, maybe on top. That's plus 2. And oxygen we know is always going to be negative 2. So sulfur is going to be plus 2 plus x plus 4 times negative 2, and total is equal to 0. So now again you solve for x, and that should come out to be equal to 6. In case of Fe2O3, Fe is plus 3, oxygen is minus 2. It's a binary compound, and those are going to be their respective oxidation states. Now, in this chapter, we are going to take a look at what is called as an electrolyte. Electrolytes, other than Gatorade, are essentially, scientifically speaking, this is a word that basically provides us, it describes a solution which upon dissolution in water is going to produce ions. Non-electrolytes, on the other hand, do not form ions when you put it in water. So you can perhaps envision that if you do have an electrolyte, and a good electrolyte at that, and you complete the circuit, the bulb is going to glow. So depending on how well the bulb glows, one can perhaps predict whether or not the particular solution is electrolytic in nature or not. So for example, if you have something like glucose, which is a completely covalent compound, or methanol or acetone, these are not going to generate ions in solution, and you're going to simply see the bulb not glow. Whereas if you have sodium chloride or potassium chloride, or for that matter a strong acid such as HNO3, these are going to have ions in solution, and hence the bulb is going to glow in these particular cases. Now, you might be wondering, what is so special that when you take sodium chloride, it dissolves? And the answer to that is because sodium chloride by itself, being an ionic compound, does have a lattice that it is present as. However, when you put it in water, basically water molecules break up, eat away the bond between sodium and chlorine, and so what you have is NaCl, and it's going to break that bond between Na and Cl, that ionic interaction that you see. And so each of the sodiums that gets surrounded by water molecules where the oxygen faces the sodium ion, likewise each of the chlorides also gets surrounded by the water molecule where it is surrounded, and the hydrogen atom actually faces the chloride. And this process is called as dissociation, but it is seen in all ionic solids that are soluble in water, and I'm going to take some time in going over the solubility rules. I have done that through a screencast. Of course, the PowerPoints are present as well, but I would want you to go over that screencast to make sure that you understand the solubility rules perfectly fine. Let's come back to what we were discussing about strong electrolytes and weak electrolytes. In case of strong electrolytes, you are going to anticipate, you are going to expect essentially a complete dissociation of the structure of the two ions when you dissolve it in water. However, weak electrolytes, on the other hand, give you a partial dissociation. So strong acids will be those which are strong electrolytes also. So something like HBr, HCl, HI, perchloric acid, sulfuric acid, these are all good strong acids, and good strong bases would be like the hydroxides, the metal hydroxides. Of course, the ionic solids which are soluble like KCl, NaCl, these are all strong electrolytes as well. Weak electrolytes would be something like acetic acid or HF or ammonia, which essentially completely do not completely go through ionization. However, you must know, and those of you who will be taking general chemistry 2 will be discussing this in greater detail. As you increase the dilution, essentially the extent of ionization gets better too, and then you will realize why. Like I said, covalent compounds such as ethanol or methanol or acetone or some kind of sugar, that will be considered a non-electrolyte. So being a covalent compound, there's no way that it is going to generate any ions. So that cannot be treated as a electrolytic component. Now, let's see.